Bear with me. Oh, it's terribly slow. Mm.
I think if you are live streaming, I think it's not required to record it separately again.
It's not. Just one moment. I'm hearing some background noise from some other things, so they might have to.
There might be some background noise on my end. I'm sorry. I'm having to join from office today. So.
Oh, you're joining from your home. Yeah. Okay.
No, I'm at the office only, and there is a little bit of noise here right now.
Why is there such noise at TCS? It seems like there's someone banging. Okay. But the reason I call, of course, I don't need to record it. I need to record on this, but I do it anyway because I'm.
Yeah, I think it's.
But I don't store it. Okay, once I make sure that it is there on YouTube. Okay, I put this thing to rest. Okay, so just a little bit of a few slides that I did not get to. So this is something you are already, a lot of you are aware, and since there is some people who haven't taken a formal logic course, I thought I'll do this. So there is this notion of normal forms, okay, that are defined. They define a class of formulas with, I'm sure we are still within propositional logic. Okay, so so it's a class of formulas, set of with some syntactic restrictions on their form. Okay, and such subset of formulas with some syntactic restrictions, they are usually called a normal form for propositional logic. If every Boolean function, notice that every formula defined, a propositional formula defined over a set of variables, since it maps each valuation of the variables to either true or false, it can be considered as a Boolean function. If it has n variables, it can be considered as an NRE function that maps n Boolean values to true or false. So it's so every formula represents a Boolean function. Of course, you can have and a normal, a set of restriction and a set of formulas said to be, so that those restrictions said to represent a normal form. If every possible Boolean function can be represented using a formula in that restricted set. Okay, so in that sense, it is universal. In some sense, it's universal. That those restrictions are still universal in that you are able to define every possible Boolean function with those restrictions by a formula belonging to that set. These are, three popular normal forms that are defined and used for Boolean formulas, propositional formulas. And first one is the conjunctive normal form. So a conjunctive normal form is a formula which has these restrictions. So say a literal L, let me define a literal L as a variable X or its negation, okay? So that's an atomic formula, either in positive form that has a single variable in positive form or negative form. That is usually called a literal in logic. And the clause is a disjunction of a finite set of literals. Okay, so that is usually called a clause. A conjunctive normal form is a Boolean formula, which is just defined as a conjunction of clauses. So a conjunction of clauses, so which means that a conjunctive normal form is built out of positive or negative literals by combining them in first with disjunctions and then taking conjunction of those things. Sometimes this this normal form is also this restriction is also called product of sums. Okay. Disjunctions can be viewed as sums, and conjunction can be viewed as product. It's sometimes called product of sums. So this is a normal form because every Boolean function can always be expressed in this form using ORs, using OR, disjunction, and conjunction, with the negation appearing only at the leaves. Okay, that's a conjunctive normal form. A disjunctive normal form is a dual of conjunctive normal form, and usually if you put the things in normal form, it'll be easier. You'll get a better handle on deciding, on coming up with a method for deciding if a particular formula is satisfiable, valid, or thing. So by putting them in these normal forms aids in coming up with algorithms for deciding Boolean satisfiability. Okay, and most SAT solvers assume that their input formulas are in conjunctive normal form, because the algorithms, Boolean satisfiability algorithms that are used in most SAT solvers assume they work on conjunctive formulas that are expressed in conjunctive normal forms. Okay, disjunctive normal form, as I was saying, is a dual of that. This is the sum. It's a sum of products. Okay, and it is constructed. Every formula in that set is constructed as follows. It starts with the literal, okay, and a cube is a conjunction of finite number of literals. Okay, so it's this is a product. Okay, so and then a DNF is a disjunction of cubes. Okay, so one can express so normal form in the sense that you can express every Boolean function. Of course, you can have, both the disjunctive and conjunctive normal forms are not necessarily unique for any particular Boolean function. In the sense, the same Boolean function can be represented there is always a formula in this normal form, but there might be several different CNF and DNF representing the same Boolean function. A third one that is very, very popular, that is the basis for a lot of, another method, very popular method of deciding Boolean satisfiability is called the binary decision diagram. It's the basis for tools that work on satisfiability, checking satisfiability based on this normal form. It's usually called binary decision diagrams. Okay, and here every formula starts, yeah, okay, so it is represented using these things. So you have constants, Boolean constants 1 and 0, okay, 1 and 0 are BDD, representing the true and false, okay. And if T1 and T2 are two BDDs, okay, and X is a variable, okay, and X is a variable, that is, it is occurring in positive form, okay. X is a variable, then X implies X. If X is true, then T1 else T2, okay. This is a ternary function whose first argument has to be a variable. The second and the third arguments can be other BDDs. So so everything is constructed starting from 1 and 0, and then using this if then else, if I may refer to, that is this particular thing that I've written here. X implies T1. If X is true, T1 else T2. So every Boolean function can be represented. Notice that this does not have negation. It's all built from 1, 0, and this if then else kind of function. For example, X and Y can be represented by nested, two-level nested, BDD form. So if X is true, then the value is, if X and Y are true, then it is 1. If X is false, then of course it has to be false. And if X is true and Y is false, then also it has to be false. Okay. So every Boolean function can be represented using this. The advantage of this BDD form, some of you may not be familiar. People who have taken logic, a course in logic, usually would have seen, say, enough, maybe at CMI, BDDs are covered as part as formal logic. People who have taken a formal logic course in CMI, are they familiar with BDDs? Yes, no? Hello?
No, sir.
Okay. So if you're seeing for the first time, this is a very, very compact form of BDD with a few more restrictions, okay? So if you restrict the order in which the variables have to be checked in this, in the BDD, in a particular order on the variables, a particular total order on the variables, then this form, BDD, is usually called ordered BDDs, signifying that the variables are ordered. Then BDDs become a canonical form, not only in a null form, but canonically, in the sense every Boolean function will be able to be, is representable by a unique BDD for, given a particular order in which you check the variables, that the order in which they are checked in the nested thing. So all BDDs are canonical in the sense it's unique. Therefore, checking Boolean satisfiability becomes, like a constant time algorithm once you convert them into ordered BDD. So there are tools. SAT solvers are one very popular tool to check Boolean satisfiability. But before SAT solvers became popular as they are in the last 10 years, tools based on BDDs were very popular. And even now, for certain applications, mostly in hardware, BDDs are the tools based on representing proposition formulas as BDD seem to win over even SAT solvers. Okay. So I think this is something that I wanted you to just be aware of. Any questions? Okay, move on. Okay, so this you've already seen. This is I've given for your class exercise. I'm not going to dwell too much on this on the slide. There are all these operators here, in addition to the ones that are used in these normal forms, and these are formulas representing various Boolean functions, and you can try converting them to CNF, DNF, and BDDs as exercises, so you will get familiar with those things. And as part of your exercise, I've asked to check if these are satisfiable and so on. So you can, I'm assuming that you already hopefully would have typed it in to Z3 to get a feel for how Z3 works. Okay, I only showed that before I move on to introducing or motivating the subject matter of today's lecture, which is first order predicate calculus with theories. Okay, multi-sorted first order predicate calculus, or first order predicate logic with theories. Okay, so why propositional logic is not enough? Okay, so just to motivate that, I'm going to ask if this is I don't know. I mean, I'm still not familiar with all the names here. So let me, rather than go through the names. So this is I less than or equal to, what do I have here? I have a problem, my I plus 1. Okay. With my display, so when I put it on full mode, I don't see part of the screen, so I'm at a disadvantage. I less than or equal to, oh, sorry, I wanted to do one by one. I less than or equal to I plus 1. Okay, someone tell me if this is satisfiable, valid, or unsatisfiable. Does it even
valid?
Valid.
It's valid.
Well, what does it even mean? I mean, is this a propositional formula?
No.
No. Okay. So first thing is, so if you want to express this, I mean, everyone assumed that I was ranging over some arithmetic domain, arithmetic type, correct? So with that, you were saying, with that assumption, you were answering your question. Okay, so you already kind of answered some of the question that, I mean, one of the reasons that I posed this question. So if I is ranging over, an arithmetic type, I mean, like int, nat, or real, which are infinite, this is not even expressible in propositional logic, which assumes that the variables range over finite domain, actually, binary domain. So in order to express these kinds of constraints that we encounter in practice, at least, I mean, even in DNNs and so on. Okay, so we want variables to range over non-Boolean, possibly infinite domains. Okay, such as arithmetic types. Okay, these domains, I mean, I use interchangeably names such as types, sorts, theories. Okay, we get to theories mean a little bit more than types. Okay, and formulas can have, so in this case, for example, less than or equal to plus, etc. They don't mean, they are not logical operators. Okay, I mean, in the sense, not Boolean operators. So they have their own, not only are they ranging over domains that are possibly infinite, and these domains have certain operations with their own meaning, which are expressed, which can be expressed as constraints. For example, I less than or equal to I plus 1, plus there actually means addition. Less than or equal to means certain things, okay? And those constraints are what are expressed. These domains, the operators, and these set of constraints are what are usually referred to as in logic as theories. Okay, theory is a set with operation, a domain, a type. I mean, a domain of values with some operations which are defined through as obeying certain constraints. Okay, which are expressed as maybe expressed in some as formulas. Okay, and yeah, we can have a Boolean structure built on top of that. Now, for example, I less than or equal to I plus 1 was an atomic formula in the theory of, in an arithmetic theory. Now you can have a formula like this, okay, which has a Boolean combinations of atomic formulas, which may have expressions that drawn from that theory. Now, if we take this formula, for instance, I'll ask the same question. Is this formula satisfiable, valid, or unsatisfiable? Anyone?
Satisfiable.
Who answers? Yeah, so you reveal your name, just for thing. I'm not going to put you on a spot, but nonetheless, I would like to hear the name as well, since we.
I'm Dhruva Jyoti.
Drib Jyoti. Okay. Well, you should be asking the questions. Is it true? I mean, it depends on the domain, isn't it? Is it true, you know, for reals? I mean, you were probably assuming that there were ints or nat, correct?
Okay. I'll have to think again a bit.
No, but now that I've explained, is that true, or have I made a mistake? If I is between 1 and between 1 and 2, includes of 1 and 2, if I is ranging over reals, okay, then I doesn't have to be just either 1 or 2. Okay, if it's reals, there are infinite number of real numbers between 1 and 2. So if it's int or nat, then it can only be either 1 or 2. Okay, because they're so that is why. So I pose this thing to make the point. 2 points. Okay, firstly, it depends on your satisfiability. Of course, depends on the domain. Okay, you should be asking the question, oh, what is I ranging over? This is true for some theories. It is not true for certain other theories. The second point, okay, so that is what the answer is. That clear? Yes. Is it clear why this is not true for reals?
So the answer is unsatisfiable, is it?
No, it is satisfiable, okay, by some, but I thought you said valid, didn't you?
I said satisfiable.
You said satisfiable. Oh, I'm sorry.
Yeah.
That is correct. It's not valid. Okay, you're right. Okay, so then I take back. It is certainly valid for integers and natural numbers, but not for reals. I'm sorry. Okay, so you were right. Okay, so satisfiability and also validity, etc. They can vary from one domain to another domain. And as you can see here, for this to be satisfiable, this is such a formula, which is where the atomic formula is drawn from theories. Both the logical structures, this is constructed. There is a Boolean structure here, okay, because there is also these logical operators, or in this case, or an implication that I've used. And there are these atomic formulas, which in the propositional case were only were ranging over propositional variables. Here, they're drawn from the theories, okay? So they have to satisfy the constraints, the semantics of the respective, of the operations used in the thing. In this case, the equality over numbers and the meaning that what it means for less than or equal to. So the satisfiability problem of formulas, where the domains are richer than Boolean domains, will have to satisfy both the logical structure, the logical constraints that are implied in this formula, as well as the constraints imposed by the theory. And that's why the checking of such formulas, and these are examples of first formulas in first order predicate calculus with specific theories. In this case, where the theories were arithmetic over arithmetic. Okay, so that is the point that I was making. And then another reason why propositional logic is not expressive enough is that we may want to express constraints that have that use quantifiers over variables. Okay, for example, if I want to state, for every I, there exists a j such that j is less than I. Okay, so these are expressing certain constraints that use quantification over these variables. Okay, so in first order predicate calculus, you can have quantification over these variables. So there will be two operators, the universal quantifier and existential quantifier, where this statement can be expressed in this fashion. Note that you can have quantifiers, for convenience in propositional formula, in propositional logic. But if the domain is finite, like it is the case in propositional logic, you can, having quantifiers doesn't really add any more expressive power, because you can always eliminate those quantifiers by enumerating those things for every element in this domain. But it still might be useful to have extensions of propositional logic with quantifiers. And the quantified Boolean logic, which I did not introduce, but I have defined in the slides that I have uploaded for propositional logic, is a logic of that kind. Okay, so although it doesn't add, it's still any real logical power. It is in propositional logic for the reason that I just now mentioned, wherein you can eliminate them by enumerating the replacing for every possible valuations for the thing, which you can do because whenever the domain is finite, in theory, okay, it is always more compact to express these kinds of constraints when you have quantifiers, and you may even have procedures. Satisfiability sometimes might be efficient even with those quantifiers to do. That's a side expression. So now I hope you understand the need for a more expressive logic going beyond propositional logic. And that's what I'm going to be, defining today, the first order predicate logic with theories. Specifically, its syntax in the way that we defined, that you saw for way defined in a pedagogic formal fashion for propositional logic, and a semantic function that defines what it means for a formula to be true is in a first order logic with theories. So this will be, that logic, you will see the semantic function will be more complex because it has to deal with the operators, semantics of the operators. Now we'll have functions over things like plus and so on. So we have to have our infrastructure. The semantic function has to give meaning for terms, functional terms, and these operators and so on. So the definition of the semantic function you will see will be a little bit more complex. Okay, so these are some of the things that first order predicate logic will have, and we will see that as we move forward. Okay. Any questions before I move to the next slide? Okay. So I mean, this slide is drawn from that decision procedure book. So so these are some examples. I mean, we will be. So now I'm talking about when I talk about SMT logic, SMT, which really stands for satisfiability modulo theory, and you will see why I keep using this term SMT or what it means when I use that term. So SMT, which is the most sophisticated, Z3 is an SMT solver. The kinds of theories, okay, it kind of sometimes restricts the kind of theories that the satisfiability that an SMT solver like Z3 is able to solve the satisfiability over. Okay, so you can have propositional logic has just the logical connectives. You can add equality over arbitrary domains to it. That gives another theory of equalities, okay, which satisfy the constraints of reflexivity, symmetry, and transitivity. Or you can have linear arithmetic of the kind that I just introduced when you have when the variables are ranging over arithmetic theories like real integers and natural numbers, okay. SMT solvers can decide satisfiability of arbitrary Boolean combinations of atomic formulas where, I mean, linear inequality formulas over arithmetic types. Like, for example, LP solvers are able to do linear conjunction of arithmetic formulas. Yeah. Okay. So, but SMT solvers go beyond that. Okay, and it also supports certain theories that are commonly used in practice, especially in programming and other kinds of things like bit vectors, finite bit vectors, arrays, pointers, and combinations of any of these theories. And this first order predicate logic with theories that are restricted to a set of predefined theories is what an SMT logic, I mean, refers to, okay, when I talk about SMT. And these theories are, SMT solvers usually are restricted to solving first-order predicate formulas for those theories, okay, the specific theories, and that's where the term SMT comes from. But I will get to defining what it means for this thing. So that is this part. So let me now start getting into how I define. Okay, so for this I'm using the slides courtesy to one Clark Barrett. Okay, I found these slides quite intuitive and compact, in the sense, in one class, if I want to cover first order predicate calculus with theories, the logic that is with theories in one class, I found these slides to be quite useful. This is due to Clark Barrett, which I'm drawing from Summer theory, in Summer School that he gave. So the author is Clark, Barrett. Okay, so let me make it go to full mode, and I'll start. Okay, by the way, this exposition will be a little bit formal with symbols and definitions and things. There'll also be some examples here. These examples are somewhat artificial that I use, and some of them are kind of brain twisters to test your understanding. But in the tutorials, Diganta will be covering more intuitive examples drawn from programs, games, and maybe even DNNs. Okay, more intuitively as to how this logic can be used to more compactly model examples drawn from these these areas of applications that I just now mentioned, and how you could model them and also ship them off to an SMT solver Z3 and solve them. Okay, so today's lecture will be a little bit more formal. Okay, and maybe the rate that I'm going, maybe I won't finish all the slides. So let's see. So first order logic, and that's what I'm going to cover here. Since this particular set of slides was a logic introduction in a summer school that was devoted for describing SMT solvers. That's why it introduces this first order predicate logic with theories as the language of an SMT solver. Okay, so as I already mentioned, SAT solvers is the logic, the language of SAT solvers is Boolean logic or propositional logic, whereas for SAT solvers is first order logic with various theories. And as I already mentioned, this is, it can have functions, like this, and predicates. So predicates are just functions that evaluate to true or false. Equality is a predicate. Okay, it's a binary. It's a function that maps to truth. So that is one aspect of extending the aspect of first order logic. So the syntax, as with propositional logic, we will start with what the atomic formulas are of first order predicate logic. And then we will build on top of that. And these symbols can have logical symbols, which are exactly the symbols that you use to construct propositional formulas. And now there'll be certain non-logical symbols. These are things that belong to the particular theory, the domain, which is or which you're constructing these formulas. Sometimes these are called non-logical symbols or even parameters in some cases. Okay, of course, the logical symbol, in addition to the propositional connectives, will also, and variables, of course, will have quantifiers. Okay, so that is something added. So the theories. The non-logical, the theory symbols are what the parameters or non-logical symbols can be. Equality, we normally assume, although equality can itself be considered as part of that particular theory, and you may have first order theories, first order logic with equality or not equality, we'll normally assume that equality is, because it's so generic that it can be defined for any domain, we'll assume that there is equality. Okay, and then you can have predicate symbols, which are just functions that map to Boolean values, and some constant symbols, which are specific elements with special, which are use special notation, specific members of the domain over which the variables are ranging. You can have use constant symbols for them, and of course there are function symbols. Okay. For example, of this kind. So, the formulas, the syntax will have to allow for these extensions. Okay? Yeah. So, moving along with the syntax, each function symbol will have to have an arity, which really defines the number of arguments that it takes. Okay, it indicates the number of arguments. And equality is a predicate symbol. It's a function symbol that maps to a Boolean value. And of arity too, it's a binary predicate. Okay, a constant symbol can also be thought of as sometimes function with zero arity, which just maps to that unique symbol. So, when you define a first order language, you'll have to specify the non-logical symbols, okay? Not symbols, first to define the syntax. Of course, the semantics, when you come to the semantics, you will have to define the actual domain values as well, okay? Yeah, so you can have this for propositional logic. If you, it does not have equality, it only has predicate symbols, which are the proposition variables. Constants, sometimes you can have 1 and 0, or you can define proposition logic without the constants 1 and 0 also. Of course, it does not have any function symbols besides these things. Okay. Now you can, for example, you can have set theory as an instance of a starter predicate logic, and membership. Okay. For example, set theory consists of equality and membership, because these elements of these set theory are usually meant to be sets, and the membership, there could be an operator to test membership inside a set, and a constant symbol which denotes maybe the empty set. Okay, and here maybe there's no function symbols. But if you're talking about an arithmetic theory, then its syntax or its non-logical symbols will include an equality symbol and a predicate symbol, a relational, representing the relational operator less than, and a constant symbol to denote 0 maybe, and then various operators such as successor, addition, multiplication, exponentiation, so on. Of course, you can, for convenience, you can also have infinite number of constants representing the various elements of an arithmetic type. That's also possible. Or this is one way, of constructing elementary number theory, starting from 0 and using the successor function, which is the can construct all the other numbers. So what I'm talking about is, now you get an idea. Okay, so before you can define the syntax of a first order predicate logic with theories, you will have to define its non-logical symbols that define the various function symbols, constants, etc., belonging to that type. Okay. Yeah. So the syntactic rules of a first order logic will have to first, define what a legal term is. Okay, what exactly a functional term is. Okay, because that is something that that you have. So we denote a function. Yeah. So this defines the rules of how to build terms. Okay. So for each function f, we have a function building term building generator, which is denoted as f of f, because so that recursively builds bigger and bigger terms. Okay. So the atomic terms are the atomic terms. Are the either the variables or thing. Yeah. So we denote the a term in this fashion. F applied to a bunch of arguments with the thing, and that's what Yeah. So, and how do you build this? So you just apply that. It starts from your atomic thing, and then which can be constants or variables. Okay. And given an n-ary function symbol and some terms, legal valid, syntactically valid terms, that are n valid terms that are constructed alpha 1 through alpha n, then the result of the term which denotes the application of f to those n arguments is denoted this way, f applied to that. Okay, and that's how the terms are built. Okay, sometimes this way of building terms recursively is called building freely generating the set of all terms from the atomic terms, which are either variables or constant symbols. Okay, so that's how the term. So the only thing here, restriction, is that the arity restriction has to be obeyed when you apply the function with that arity to those many terms. Okay, so fancy way of saying your terms were to be syntactically valid, as you can see in the language. Okay, and then you have a way of constructing the formulas. Okay. Yeah, so I'm just getting distracted. Yeah, sorry. So similarly, you have to have, so here you define, by defining a formula constructing operator denoted by this epsilon symbol. So what are the atomic formulas in this case? In the case of propositional formulas, the atomic formulas were just the variables. And if you had constants in the allowed constant in the logic, it was 1 or 0. So here, the atomic formulas, in addition to those logical, propositional logic terms that you can also have the atomic formula can be a predicate applied to T1 to a bunch of terms. Okay. Because a predicate, as you know, is something. The predicate symbol is used to denote a function that maps, a bunch of arguments to either true or false, and therefore, a formula, an atomic formula, must be some entity which is meant to give true or false, and that's why predicate is meant to denote one such thing. So a predicate with an arity n applied to n terms is a new form of atomic formula in a first order logic. Okay, for example, the equality symbol is a predicate symbol. Okay, it's a binary predicate symbol, and that can be a formula. So that is starting with that atomic formula. Then you can now construct all the other things. Okay, just like you did in propositional logic using the logical connectives. Okay, so that is done exactly the same way as in propositional logic. Okay, so you have the negation. If alpha is already a syntactically valid formula in the logic, then you can put a negation around it and then construct a bigger valid, first order formula. Okay. Similarly for implication and not and other logical connectors, these are exactly similar to what you had in propositional logic. The only new thing that you have here is a quantifier. You can apply, given a variable, given a variable, v, you can, I don't see, given a variable vi, you can now, so you can put the universal quantifier in this case, okay? You can construct a formula that has this form. So say that for all v, that's how you read it, for all values that the variable v is ranging over, alpha should be true. Alpha is usually meant to be a formula that contains this variable. This is how you syntactically construct formula with a quantifier. Okay, so the way we are defining this logic, we only show you the universal quantifier, because an existential quantifier is not formally introduced. You can have logic that introduces explicitly an existential quantifier, but since usually an existential quantifier is assigned the meaning, is considered as, can be expressed as a negation of a universal quantifier, as you will see in the way that the semantics is defined. That's why in the syntax we only include for all, and by expressing the existential quantifier as a negation of a using negated universal quantifier. Okay, just like you could do, with sometimes you can have you can have only a subset of the logical connectives. Okay, if you had negation, you can express certain other in terms of certain logical connectives as derived operators. So that is how this we define it here. Okay, that's why existential quantifier is not explicitly introduced as part of the syntax. Okay, the set of well-formed formulas. Okay, it's the term that we used. Is a set of expressions generated from the atomic formulas constructed from the non-logical symbols using the rules of construction that we just defined, okay, for the formula constructing operators, okay, and these three rules that we just saw. Yeah, whenever it is constructed in this fashion, it is said to be freely generated. Okay, so here are some examples. Okay, so I'm going to go. It's 5:58, and let me go till 6:15. Okay, since I started a little bit late, is that okay? If I went till 6:15?
Yeah.
Okay, I did not.
The time is anyway still 6.
Was that a no? There was some echo.
No, I think.
Actually, it is fine.
Yeah.
Yeah, I think the original time was also 6:15 only, so I think it's fine.
Is that right? I mean, I thought that technically it is 1 hour 15 minutes, is it? Or 1 hour 10 minutes? I don't know.
1 hour 10 minutes, but so I think 6:15 should be okay in this particular case.
Okay.
We published it at 6:15.
I think without guilt, I can do it. Although it's Janmashtami, well, that may be the thing. Because you guys came 5 minutes late. Some of you, I shouldn't say all of you. Yeah, so Adi's question is, yeah, of course, before you say you can have examples of formulas, we have to define what your atomic, non-logical terms are. Remember that we already introduced the elementary number theory, okay, with successors and so on. Let's assume that that's the non-logical operators that we are constructing the formulas over. So answer. So the answer is, which of the following terms that I'm going to show in the list that I will show, you have to answer. So is this a syntactically well-formed term, assuming V6 is a variable? Yes or no? Quick.
Yes.
Okay, good. Yeah, because a variable is a term, as we have defined, it's an atomic, right? So that's why. So V2 plus V3. Okay, so this is an S2 because plus is a legal non-logical operator belong to the elementary number theory as we have defined. P1 and P2, is this a legal term? The important thing is if it's a term, okay? Yes or no? I'll give only a couple of seconds. Okay. Why is there a silence? See, it's just kind of a trick question because, not a trick question by that tricky, terms are drawn only using non-logical symbols, and other than, of course, variables and non-logical symbols. Okay, so this has a logical symbol. The moment you have logical symbols, this is an AND of two, P1 and P2. So this is a formula in the logic, but not a term. Okay, that's why it was tricky in that sense. Yes, it is a formula, but not a term. A term is supposed to have only a constructed using, it's a non-logical entity, okay? An entity that is constructed using non-logical symbols. And so it's a logical symbol. The moment you get to that level where you're constructing expressions in the logic that contains logical connectives, they can only represent formulas. Okay, so we have introduced terms and formulas as two separate syntactic categories. And that's why this is not a term, but it is a formula. Okay, so atomic formulas. Now, are these well-formed atomic formulas? Is this a well-formed atomic formula? Yes or no? Why is it complaining? Oh, it's already that way. Okay. So it's an equality. Equality takes two arguments. Therefore, it is the arity is fine. And it has to take two terms. So this is a term because you remember that elementary number theory had plus and had a constant 0. This is a variable and it is raised to the power of V2. It has an exponentiation operator. So this is a legal term. And the right-hand side is a legal term too. So S applied to V3. And therefore, this is a valid formula, okay? Because this is a valid formula and this is an atomic formula. That's the question that is being asked. It's an atomic formula. An atomic formula, as you know, the way we define, is constructed out of the predicate symbols in the thing. An equality is an atomic predicate, is a predicate symbol in that theory that we introduced, okay? And so that's why it is, okay? Is this an atomic formula? Anyone?
No.
Yeah. Yes, this is a formula, yes. It's not an atomic, it's not an atomic one because it has, it is constructed using logical operators. So is this well-formed formulas? Okay, so this is, yeah. Why is this not a well-formed formula? I think this should be yes. Yeah, this is certainly a well-formed formula because here I'm not insisting it to be an atomic formula. V2 is equal to V3 is a formula, okay? And so a negation over that, this should be yes. Okay, that's wrong. Yeah, the second one is a no, because it's a term, yes, but not a formula. A formula should be constructed. It should be either atomic or constructed. It should be something that takes logical truth value. So you can't. Yeah. So this is not. This is a term, but not a formula. Let alone well-formed formula. Now this one, anyone?
Yes.
Yes. Okay. Good. Yes, that is. Yes, because it has a variable, that is, it is quantified over, and just checks if these two are equal. It's expressing that constraint. So you got the idea. Okay. So another syntactic concept that I have to introduce. So the moment you have things like this, okay, for all thing, when you have your quantification, there is quantifiers, and you can have nested quantifiers, okay, because after all the formulas are constructed recursively from smaller formulas to bigger formulas, and so you could apply for all you can nest these kinds of quantified formulas within other formulas that are quantified over variables, and therefore you can have nesting of things. Therefore, these variables define scopes, okay, just like scoping in a programming language. And when you have that, there is this notion of because each quantifier there's this notion of that it binds that variable that appears within the nested formula, okay, to a particular thing, and that notion is usually introduced using this notion of free and bound variables. So we define what a free variable is, also in a bottom up fashion, recursively. Okay, so if alpha is an atomic formula, then X is any variable that occurs in it is said to be free in alpha. Okay, note that an atomic formula is something that does not have any quantifiers. Okay, so any formula that does not have quantifiers, all variables that appear in that is considered to be free, because it is not caught or bound or caught by any quantifier. And so an atomic formula is free of quantifiers, that any variable that appears in it is considered to be free. Now, if this is now a non-atomic formula, negation applied to alpha, and X is occurs is assumed to be free. If X occurs free, X is said to be free in this composite non-atomic formula if X occurs free in alpha. Okay, but if X is not free in alpha, that it is caught by some bounds, then it is not free. Okay. Similarly, for these formulas, if X occurs free both in the antecedent and consequent of the implication, then you have X is assumed to occur, S is said to be free in this whole formula. Now this is where it gets interesting. Sorry, yeah, yeah. X occurs if now it's if is it X? No, what do I have here? A V, yeah. If V is okay. Now here is a formula which quantifies this particular variable Vi. Okay, so in this formula now, if you ask the question if X, a variable occurs free in this, that depends on whether X is caught or quantified as the same as Vi. So that says if it is assumed to occur free in this, if X occurs free in alpha, if it occurs freely in alpha, and if X is not this particular variable Vi, then X occurs free in this quantified formula which quantifies variable Vi, which means basically X occurs free if that X is not caught by this particular variable. Okay, so yeah, and there's this concept of then Vi is said to be bound in alpha. Okay, if it is not free. Yeah, so if there is, if a particular variable is quantified in a formula, then that variable is said to be bound in alpha by this particular quantifier. Okay, so that is it will be bound. Not only it is bound in the sense it is caught by some quantifier. And that particular quantifier which introduces that is said to be the quantifier that binds that variable. If no variables occurs free in every variable in a formula, okay, is bound by some quantifier operator that appears in that formula, then such a formula which does not have any free variables, okay, that means that everything is bound, is said to be a sentence. Okay, so that's a technical term that is used for formula. Okay, and let me see. So what is the time now? It's 11. I still have 4 minutes. So sometimes you have, I just want to introduce, there can be clash of names, just like in your scoping. For example, here, I hope you can see this. Consider this formula that I've highlighted here.
So could you make the font a little bit bigger?
Yeah. Better?
Yeah, I think this is much better. Thanks.
Okay. Yeah, take the first example. Now, I've asked the question if X is free in that. Is X is free in that? You see, I mean, yeah, I mean, technically it is kind of because it does appear. See, there is, so here, X is actually in this sub formula, X is not free, okay? Up to here. Because X is bound here. I mean, in logical things, this is a well-formed formula because that the definition that I gave there, it does not preclude such repeated variables, okay? But sometimes, yeah, but this X here, although I've used this X because it is appearing outside the scope of the embedded, this universally quantified for all, it is technically a different variable, okay? It is technically a different variable. And therefore, I mean, in order to avoid this confusion, one, you know, sometimes in logical text, they say, oh, we will assume that, you know, yeah, you can, yeah? Was there a comment? Oh, okay. Yeah. So just imagine this X is something you know, meant to be different. So this can be ambiguated. So it's X kind of occurs free in this. It does occur. I mean, you could say it occurs free and bound, okay, because I'm using the same variable. But you know, this is the meaning of this is as though in the, you know, if you know, having this as some completely different variable, and that's why, I mean, here for all, you know, for all X there exists an X such that X is less than or equal to X. I mean, you usually shouldn't be writing these kinds of formulas from a you know, to make it really clear, because of course X, the inner X, these occurrences of X here, they are bound by this particular exists, okay? And therefore, in this case, there does not happen to be any X at all in the outer scoping. Therefore, you might as well throw this for all X, for all you want, okay? For all you care. You know, but for example, here, I do have an X here and another X here. So the X's that appear here, they're actually bound by this one, and they have, you know, they're meant to be denoting a separate variable than this, than the X here, which is associated with the outer scope. So in order to disambiguate these kinds of situations, we may assume that you know, there is no you know, clashing of variables within the scope and so on. So I just wanted to mention this as a side thing because, you know, this is a technicality, and sometimes you know, these definitions, etc., gloss over this, and you know, that it might kind of stump you in some cases. Yeah. So any questions so far before I yeah, I will, yeah. So if there's no question, so I'll only take a couple of minutes. Oh, 6:15 already. So then maybe this is a nice place to stop and ask any general questions that you may have. Yeah. Have any questions? I mean, regarding, I guess, I mean, are all 6 of you signed up? For sure. That's a question I have.
I have registered, yes.
All 6 of you have registered. My question was, since are you surely signed up for the course? That's what I'm saying. That's what I'm asking.
I'm Devorshi here. I'm an external candidate actually. I'm from ISCS. So I told you that I'll be doing the course.
Ah, okay. One of you is that. I mean, I was assuming that you were, oh, so there are 5 of you from CMI. I guess this is relevant for CMI, you know, people. Yeah. CMI registrants. Yeah. Hello?
Hello, yeah.
Yeah. Anyway, so that's just a general question. Of course, you have till.
I think people are saying yes in the chat. So I think the only person who has.
Okay.
So I think one person from, yeah, Nabeen, are you registered? Like, just for.
No, but Nabeen is a CMI.
Yeah, I have registered.
But Nabeen is also not a CMI.
No, Naveen is from CMA. Naveen is from CMA.
Abhi is registered. I know everybody, all the 5 people here are not only enrolled, but also on the webpage, but they are registered. I said 6, but of course, I made mistakes. One of them is external registrant. Okay. So for that person, this question does not apply. Yeah, so there are 5 people from Smile. Good, and then 1 external registrant. Yeah, yeah. So some of you might find these things, maybe if you've taken a logic course, then this will be a little bit of rehash. But I thought that it would be useful, for us to be sure that these concepts, logical concepts, we are aligned on that. We have the same, meaning to it and so on. It's always useful to brush up on logic, concepts and semantics, no matter, even if it's a repetition. And I hope you appreciate that. Yeah. And so please ask questions. I mean, if you are, unfamiliar with it, or if I'm, explaining it slightly differently than the way that you have understood it, I think you should ask questions. And even if you're not asking questions here, you can feel free to ask questions in the tutorials if you have any doubts and so on. Okay, so with that, I will end the I'll stop sharing. I'll end recording. And